This is section 4.2 on the least squares regression line, which is a mouthful. I usually call it the LSRL. And this whole section is about an equation for a line that goes through what we call the center of the scatter plot. And this helps us predict outcomes within the domain of the given data. So it's kind of a long sentence. An equation for a line that goes through the center of the scatter plot to help us predict outcomes within the domain of the given data. This is a very powerful line. Some places call it the predictor line because we're going to make predictions and projections off of this. Businesses use this all the time to help them anticipate what's going to happen down the line or anticipate where something started. So it's a very powerful tool given a scatter plot. Given two variables that you're trying to compare, we use this regression line to help us make predictions. So the least squares regression line, or the LSRL, is more commonly known as the line of best fit. You might have studied this in your grade school studies, the line of best fit. Sometimes it's brought up in an algebra class and sometimes it's not. Scatter plots are algebraic equations, and so you can discuss these in an algebra course. The line of best fit. So it is a line that goes through the scatter plot in a way that the distance between the line and the data points is minimized. So it's called least squares regression line because we're minimizing the distance. So we find the least or the smallest. It always goes through the mean or the average for each variable. So it always goes to the point x bar, y bar, which remember that's the average for the x values and the average for the y values, which is always smack dab in the middle of your scatter plot. So the line always goes through that point. The vertical distance between a data point and the LSRL is called a residual. We don't discuss residuals too much, but I want to show you what it is, just in case there's a homework question in, so that you better understand where this LSRL is coming from. So it's called a residual. And I think it's best explained visually. So here's the same scatter plot of the club head speed and the distance. The same one we were discussing in section 4.1. Here's our scatter plot points. And we have found roughly, I just kind of eyeballed this, a line of best fit. And a residual, if you pick a data point that's not on the line, let's pick this one down here, the distance between that data point and the line of best fit, that is called the residual. If the data point is below the line, it will be a negative value. So that would be a negative residual. This would be a negative residual. Any others below the line of best fit is a negative residual. Any data point above the line is going to have a positive residual. So that would have a positive residual, that would have a positive residual, and that would have a positive residual. The further away the point is from the line, the bigger the value. So on your formula sheet, you'll see a place that says residual. It is the observed y value minus the predicted y value. And so it's the observed data point, and it's the difference between it and the predicting line, or the LSRL. So the book has a nice picture of this. It gets a little bit more specific. It has the actual values on the predictor line and the actual values of the data point, and it's subtracting the y values. It's taking the observed y value and subtracting the predicted y value, and it gives you a positive residual because this data point is above the line. I won't make you calculate that by hand. If I took every single residual top and bottom from all of these and added them all up, positive and negative, they would add up to 0 because they would balance themselves out. So just a little bit of information on residuals. Alright, so the reason the line of best fit is called the least squares regression line is because it minimizes the sum of the squared residuals. Now again, we don't get into all of that. You don't ever have to calculate any of that by hand. The calculator does all of that for you. The book goes into great detail on how to do all of that. Don't worry about any of that. Just know that that's why it's called the least squares regression line, because it squares the residuals. Kind of like standard deviation, we squared those differences. Same idea here, we're squaring those residuals, those differences. So this creates a line that can be used to make predictions within the domain of the data. So we have to stay in the domain that the data is covering. And the equation for this is y with a little triangular top, and we call that y hat. It's kind of like x bar. It's not very creative. It's just y hat. And then we have what's called b naught plus b1 times x. Now in algebra class, I think you used mx plus b. It's the same idea. The number attached to x, which in this case is b1, is still called the slope, just like it was in algebra. If you remember, m is the slope. And remember, this constant is the y-intercept. And it's the same thing, except b naught is first, and it's called the y-intercept. So it's a little switched than it was in algebra. But it's the same idea. You have an initial starting point plus a slope that changes every time x changes. So it looks a little bit different, but it's just like y equals mx plus b from algebra class. It's just that mx and the b are switched. Instead of calling it m, they call it b1. So it's not really new. It just looks a little bit different. And instead of just having a y, we have what's called y hat. Y hat is a predicted y value. It's not the actual y value, it's just a prediction. Alright. So how to calculate the LSRL, it's on page 197 of your book. If you have what we call the raw data, you use the calculator, you put your data in L1 and L2, which we've already done, stat calc 8, which we've already done. If you do that, I still have it up on my calculator. You can see that it says y equals a plus bx. A is your y-intercept and b is your slope. So we can write that down. Let's round. Y hat equals negative 55 point, that would round to 80, plus 3.17x. So you just read off those values, round them off as appropriate, a and b. B goes with x and a is your constant. So there's your line of best fit. If you only have the statistics from the data, which I think there's a homework question, I'm not going to make you do this by hand on your test, but you have to manually calculate the LSRL using these two formulas, which are on your formula sheet. There they are. There's how to get B1, and there's how to get B naught. It's a little tedious, but it's just kind of a calculation. It will give you all of these numbers. It'll give you R, it will give you the standard deviation of Y and the standard deviation of X. It will give you Y bar and X bar, and you just kind of what I call plug and chug. Most of the time you'll be able to use option 1. I think there's a couple in the homework where you have to use option 2. Alright. I believe the next slide has us just run through that once. Normally we can just get the equation right off the calculator. Let me just show you once how to use the statistics. So let's pretend that we do not have the data in our calculator. We don't have this to use at all. They just tell us those pieces of information. So we're just going to use the formula V1 equals R times S of Y over S of X. and you just type it in. R is 0.9387 times S of y over S of x. This will give you slightly different values, but not too difficult. You just type it in. Use parentheses here so that it divides first and then multiplies. Whoops. Hopefully you can see that. It's going to be a little bit different because of the rounded values. And so we get 3.217, which is slightly different. The computer will know if you're using the formula that you're using rounded values, so we'll already adjust for that. And that's B1. That's our slope. And then B naught is y bar minus the number we just got for B1 times x bar. So y bar is 266.75 minus B1, which we just got, times x bar. This is just tedious. Don't let it confuse you. It's just typing in numbers. So I'm just going to type that in, 266.75 minus 3.217 times 101.875, and it should give you negative 60.98, which again is going to be a little bit off. So you would get y hat equals negative 60.98 plus 3.217x. I know that's kind of a pain. Most of the time you won't have to run through all of that. Most of the time you'll just be able to do stat calc option 8 and be done. But there it is if you have to work it out by hand. Alright, so we get the LSRL, and it really helps us do a lot of things. Maybe, there we go. So we like to use the LSRL to make predictions. Usually businesses like to use these to make predictions. The medical field makes predictions using these types of projections, so they're really powerful tools in helping us try to predict or anticipate what's going to happen. So we want to calculate what is the predicted distance for a club head speed of 104 miles per hour. Now let me go back to that original set of data. I'm going to fold this back so we can see it. Here's my original set of data. Club head speeds ranged from 99 up to 105. So 104 is in the domain. Our data came from 99 to 105. That means 104 is safely in our domain. So we can use our LSRL to make our prediction. So I'm going to use the one from the calculator. Y hat equals negative 55.80 plus 3.17x. So this is my x value, so I'm just going to plug it in. Times 104. Let the calculator do the work for you. Negative 55.80 plus 3.17 times 104. And it will give me a predicted distance, 273.88. And that's it. Just plug it in, get an answer, if it's in the domain. Now the second question says, what is the predicted distance for a club head speed of 80 miles per hour? Now a lot of the times we just jump in and plug in 80, but before we do that we have to go back to our original set of data. Is 80 in our domain? Not even close. The slowest speed we had was 99. So 80 is outside of our domain. So even though we could plug it in and we could get an answer, that answer is not very reliable because we don't know what's going to happen outside of these outside of these club head speeds. If you swing too slow, something totally different might happen. If you swing faster than this, something totally different might happen. We can only stay in this safe zone between 99 and 105. So instead of actually calculating it, this is outside of our domain. So we would say cannot be calculated. We cannot use the LSRL that we got to predict something that's outside of our domain. And companies do this a lot. I know Cy-Fair ISD here in the Northwest Houston area over-predicted how fast they were going to grow. They had their growth rate, and they used a prediction line to predict 10 years outside of their domain, and they were very wrong. So they got a lot of money and built a lot of schools, and then those schools did not fill up because they overextended their predictions. It's called extrapolation, if you've heard that word before. Extrapolation means you're going way far beyond your domain, maybe too low or too high, and the prediction line that you were using does not fit outside of your domain. So extrapolation is the word for that. I don't know if this textbook mentions that word, but that's the word that's used when you're going outside of your domain. All right, so using it to make predictions. And the last thing we need to discuss is how to interpret the slope and the intercept of the LSRL. So the slope of the LSRL tells us how much the response variable, or the y variable, increases when the explanatory variable, or x, increases by 1 unit. Now that unit depends on the problem. It could be gallons, miles, inches, whatever it might be. For the golf scenario, for every 1 mile per hour faster the club swings, so that was our x variable, 1 mile per hour faster the club swings, the distance increases by approximately, now we're going to go back to our LSRL, and our slope is 3.17. Whoops. So 3.17 is how much the y variable changes every time the x variable goes up. So I'm going to say by approximately 3, and I believe it was being measured in yards. So approximately 3 yards. So for every 1 mile per hour faster the club swings, the distance increases by approximately 3 yards. So I took our slope of 3.17 and I just rounded it off to 3. So that's just kind of interpreting what the slope means for this particular situation. And the y-intercept, is only appropriate in some scenarios. It tells us where the response variable starts when the explanatory variable is 0. For this scenario, when the club head speed is 0, now let's think about this. That means you're not swinging the club at all. You're just standing there. No speed on the club head. It does not make sense that the ball will travel, look at this number, negative 56, so it's negative 55.80. I'm going to round that off to negative 56. It does not make sense that if you don't move the club at all, you're just standing there, the ball will not magically travel backwards negative 56 yards. So in this situation, the y-intercept does not make sense. You have to decide, given the scenario, given the value, does it make sense for the situation that when the x variable is 0, that the y variable is whatever that number happens to be? If you're having trouble with that, just let me know. You just kind of have to think about each situation as appropriate. So you have to determine for each scenario if the y-intercept is appropriate or not. Should be fairly clear. If not, just email me. Alright, and that finishes up chapter 4, not too long at all. So we know how to draw and interpret scatter plots. We can compute and interpret the linear correlation coefficient. Remember, that's the R value. We can determine if a linear relationship exists. That's that chart of critical values that we discussed. That will not be on your test, it's just on your homework. Find the LSRL and use it to make predictions. Remember, it has to be inside the domain. And now we can interpret the slope and the y-intercept of the LSRL for a given scenario, so it's very specific. Objective 3 from section 4.2 we are not covering. And remember, we're only covering sections 4.1 and 4.2 from chapter 4. I think there's 4.3 and 4.4 that we do not cover. So nice and short, just half of chapter 4.